MKEL 1123.05 Milestone 4.
Hi, my name is Muhammad Shafiq Alim, entry number MKE 2111062.
Hi, my name is Azida Izzati binti Abdul Basit and my metric number is MKE 211068.
My name is Umi Nur Idayu binti Muhammad Hisham. My metric number is MKE 211073.
Hi, so this is a phenomenon detection device design based on embedded technology and CMSIS neural network. As an introduction, we have a 4.57 million cases of COVID-19 with 35,000 as deaths as of 3 July 2022. About 50% of these COVID cases is related with pneumonia. Pneumonia, however, can be easily detected from an X-ray image from the patient. With that in mind, hospitals around the world must have been bombarded with numerous X-ray images just to identify pneumonia. This hassle task can be simplified by using a CMSIS neural network, so we can automate the detection using machine instead of manual observation by the doctors. However, the majority of terminal usage device that is used right now is sophisticated equipment that is invasive but powerful. So the objective of this model is that to create an artificial neural network based on phenomenal detection device using an edge-device platform for an embedded application. As a proof of concept, let demonstration of prototype using an STM32 development board and the 10 phenomenal detection device for neural network that it has been done in earlier point. With that, we will carry out accuracy-based performance measurement and system functionality verification.
Okay, for this project, we uploaded around 1000 X-ray images from Kaggle to this Edge Impulse, and we split 81% of these images to train and 90% for for testing. So which means that 561 X-ray images for pneumonia and 442 items for normal images. And then we need to create the impulse. So for creating this impulse, the image data need to set by 32 by 32 for width and height, and the classification we use Keras, which is NN classification. And then for the image that we upload, we need to set the parameters, which is grayscale for this project, and need to generate the features which for all the data that we uploaded. And when we want to try our model, we need to set 100 number of training cycle, 0.005 for the learning rate, and 20% of validation set size. After we train and the result is we have 97% of the accuracy, and the peak RAM usage we have 43.9k, and flash usage we have 40k. And then after we train the model and we need to test. So for our testing, we got 93.31% of accuracy. And lastly, we need to deploy to this cube.ms, which is STM32, for so that the STM32 have this model to detect whether the X-ray images have pneumonia or it have a normal lung. After we try on the STM32, we need to have our live classification. So for our live classification, we use the existing test sample. We just pick a random images and generate its raw features. Because these raw features we need to we need to include it in the coding at STM32 Cube IDE. And I think that's all for the Edge Impulse.
After the dataset training is done, the trained model can be deployed into STM32 board by generating CMC spec from the edge impulse. The CMC spec will be used as the main library for the pneumonia detector. The web file here is very important because there is a edge impulse CMC file that connected to neural network data and where is the main program is located. For the coding, first one we need to include the EI-run classifier, and then we need to initialize the array that we use. Here we initialize the get feature function to import the important features for the data, and then we go straight to our main part that is inside the while loop. So here we initialize again the above feature, that is get feature data. First, the function will check the error inside this run classifier. If the parameter meet the error requirement, it will tell the user there is an error and it will stop running. The error that usually come out is the make file 123. We need to meet the size requirement before running the code. If there is no longer error, it will print the timing of the DSP, classification, and anomaly in milliseconds. In the prediction, the first function is anomaly. Why we put this function? This function is to detect the foreign features that are outside from our trained model. If we put correct model, this code can be skipped and jump straight to the compare pneumonia lung and also the normal lung. If the percentage classification of detection pneumonia lung is higher than normal lung, it will print this is pneumonia lung. Else, if the percentage classification of detection normal lung is higher than pneumonia lung, it will print this is normal lung. Else, there is an anomaly, it will print this is uncertain value. Next, I will show you the demo to run the project using the STM32 board. First, in the normal sample, that is a normal condition, click on the hammer icon on the top side to compile the project. If there is error, fix the error and rerun. Make sure the compile pass and it is free from errors. And then to upload the code into board, click on the play button icon. Leave all the settings to default and make sure you already connected your board prior clicking the play button icon. So here, this message will show if you have successfully uploaded your code into the board. To display the output, open PuTTY and then choose serial as the connection type. Set the speed into 115200. And then choose COM3. And if you want to know which COM that you need to use, open Device Manager to check. So here is the setting that we use. The result will be shown on PuTTY interface. So the result showed this is a normal lung. And then for the second condition is a pneumonia lung. Again, click on the hammer button. And then after build finish, click on the play button to connect the code and to the board. Download verified successfully, shutting down, exit. The result in PuTTY shows this is a pneumonia lung. To change the data set, we can copy the raw feature of each image. To do so, go back to each edge impulse at the left side, choose live classification, And under existing test sample, choose which image you want to have its raw feature. Then click the load sample and wait for the classification results come out. Then copy the raw feature and paste it into this line of code in main.cpp. That's all from me. Thank you.
As you can see, this is a tabulation of test samples that has begun using the features that has been activated from task classification in Edge Impulse. You see that for the fourth and the ninth image, the output is different from what we expected, and this has given us an accuracy of 80% for the whole model using the CMSIS neural network.
Thanks for watching.